Hello, my name is Viraj Thakur, and I'm here to present to you my final project, HBase, a real-time column-oriented database. HBase is a distributed, scalable, column-oriented data store on top of Hadoop. It has been modeled after Google's Bigtable and is written in Java. HBase is developed as part of Apache Hadoop project, and it provides a fault-tolerant way of storing large quantities of sparse data. HBase uses Hadoop for its data store, and hence it's very distributed, and data can be stored over a large number of commodity servers. It scales horizontally by adding more machines and nodes or region servers, and it is a columnar store. Looking at an example of 4 publicly traded stocks by daily data, a DBMS system would assign a unique row ID to each row and stores the entire row on a single block. It is designed for efficient and fast single row read-write operations, but falls short in coding at summarizing and aggregating across the entire dataset. On the other hand, on the right-hand side, the columnar store, the same data is stored differently in that the column values are stored together. This model is a key value pair model and is very efficient for reading data for entire dataset on a small set of columns. Column data is stored on a single block, and hence aggregation on column is much faster. It is designed more for OLAP queries. It also offers a high degree of compression due to few distinct values or sparse data. Well, on the downside of this model, it is not efficient in reading the entire row data, especially if there are a large number of columns. To understand HBase a little bit better, it is important to understand its differences from a relational database. As already discussed, HBase is column-oriented, and in addition, it is schemaless in that one does not define the types of columns and even the number of columns up front. Everything is stored as byte array, and since columns can be added on the fly, there is no downtime for DDL changes in HBase. HBase is designed for tall and wide, billions of rows across millions of columns. HBase scales by adding nodes and machines, whereas a relational database scales vertically by adding more CPU and RAM to the server. HBase is best designed for read-write and real-time access to analytical queries, whereas the relational database is used for read-write OLTP-based transactions. HBase does not support a SQL or SQL-like language. Clients access HBase via Java or Thrift APIs. There is also a shell interface and REST interface to HBase. Whereas a relational database supports ANSI SQL, and it is a very well-known and established language for querying databases. So why do we need HBase if we have Hadoop? HBase provides a fast, real-time access to data, whereas Hadoop by its very nature uses a MapReduce, which is batch-oriented in nature. HBase is built for performance and provides low latency responses to queries. Hadoop, since is a batch processing system where the user submits jobs and is notified when the job completes, it is a high latency model. HBase is very efficient at reading single to small range of rows from billions of rows, whereas Hadoop is typically best used for reading entire dataset. Hadoop is a random read-write model, whereas HBase is a random read-write model, whereas Hadoop is a write once, read many model. Therefore, the use case for HBase is fast, real-time, random read-write access to petabytes of data. Let's look inside HBase's architecture. HBase is built on top of Hadoop and stores its data files in HDFS. Hence, it offers all the benefits of Hadoop, that is fault tolerance, distributed, horizontally scalable, and runs on commodity hardware. HBase is designed to handle vast amount of data to the nature of petabytes. Zookeeper is another open source project under Apache Software Foundation. HBase uses Zookeeper as a coordination service. HBase follows a master-slave paradigm to an extent, wherein the master monitors and assigns the region servers or the slave nodes. However, the master is not on the data path and hence is not a bottleneck to client queries. The actual work is performed by the slave nodes or the region servers, which are responsible for managing one or more regions. One of the benefits of HBase is that it provides auto-sharding or partitioning of data into regions as the data grows. A table is partitioned into roughly equal number of partitions called regions, and each region is assigned to a region server across the cluster. A region server can hold regions of different tables. Each region server holds roughly equal number of regions. Inside region server, a region server contains a single block cache, single write-ahead log, and multiple regions. Block cache serves the read operations and holds any data that is needed to serve queries for a short period of time. Each region server writes updates such as put and delete to write-ahead log and then to memstore before memstore gets flushed to H files. This is for durability, such that if region server were to go down before writing to H file, the data is still available in write-ahead log. Regions are the basic element of availability and distribution for tables. These are comprised of a store per column family. The mapping of regions to region server is kept in a system table called meta. When trying to read or write data from HBase, the clients read the required information from the meta table and directly communicate with the appropriate region server. Each region server has multiple H stores per column family of the table. H store holds zero-to-many store files and a memstore. The memstore holds in-memory modifications to the table until it is flushed to store file. Memstore holds data in the form of a key-value pair, and H file is ultimately where the data lives. HBase's data model is actually quite simple. It is comprised of tables, which are declared at schema definition time and are sorted by row keys. Everything in table is stored as byte arrays and there are no types. Row keys are byte arrays and are lexicographically sorted. Indexing is by row key only. Atomicity is guaranteed at row level and not across rows, and hence transactions are not supported. Column families are simply a group of columns and their names must be printable. These are declared at the time of table creation. Columns are identified by the column family and a qualifier. There is also a concept of versioning with the help of timestamp on each column value. HBase maintains versions of values similar to a slowly changing dimension concept in dimensional modeling world. A cell is uniquely identified by row key, column, and its version. Now let's understand the HBase data modeling with a concrete example. The dataset is a daily view of stocks performance of 4 publicly traded stocks. To understand the data model, we have to first understand the questions that will be asked of the system. The questions I came up with are, what is the most recent volume for a given symbol? What is the stock performance in past 2 days? What is the latest high-low by stock? And what is the performance of stocks on any given day? So the access pattern for these questions are stock performance metrics by stock symbol and date. In a dimensional modeling world, stock symbol and date would be the dimensions, and the metrics are volume, open, close, high, and low. So in this kind of a model, what should be the key? Recommendations for key design are that the key should contain the dimensions in query for quick access. So I came up with a key where I concatenate the symbol with the date. And once I order the table A to Z, the row for each symbol, the first row for each symbol is the oldest row. With this kind of a model, can I answer what is the most recent volume for a given symbol? To address the most recent problem, it is recommended to use reverse timestamp for the date portion of the key. I assigned a reverse timestamp manually for my prototype, and such that the most recent row actually gets a lower value than the older row. Now when the table gets sorted A to Z, my most recent row for a given symbol is the first row. What should be the column families in this model? I came up with two options, and considering the recommendations, I chose option B, where all columns are in a single column family. To implement the model, I chose Amazon Web Services cluster with HBase installed and running. To connect to the master node, I use Sigwin, and I run the HBase shell using the HBase shell command. To implement the data model, there are some simple commands like create table. Create stocks perf creates a table called stocks with a column family perf, and you would notice I did not define any of the columns at the time of table creation. The describe table describes all the options that are set for the table, and here you would notice that the block cache by default is set to true. There is a single column family called PRF, and there are 3 versions being maintained by default. The put command is an interesting command in that it also does an insert and an update. The first command, put stocks apgpl_1, inserts a row into this table stocks with a row key of apgpl_1 and adds a column called sim to column family PRF with a given value. There are some other commands that you can use to count the rows in a table, to select all the rows in the table, or to get a particular row out of the table with its given key value. But what about my use cases that I set out to solve? The first use case was, what is the latest volume for a given symbol? To get that kind of an answer from HBase, I scan the stocks, the table stocks, and I return columns sim, date, and volume from the column family PRF, and I limit the row by only selecting the first row, which is like a top 1 paradigm, and I do a key range scan on the key with a prefix of FB, essentially returning me the first row for where the key starts with a value of FB. The second use case, what is the stock performance in past 2 days, is a variation of the first one, where I'm selecting the top 2 rows and doing a key range scan, partial key range scan on key starting with FB. The third use case is also kind of a variation on the first two, but here the change is that I select particular columns, high-low columns, and the symbol and date columns. My last use case, what is the performance of stocks on a particular date, is different from the other 3. I'm actually looking for a particular column value. So what I use is a filter expression where I filter a single column value filter on column family PRF for the column date with a comparator equal to, and I'm matching a string which is the given date. Return to show you that I'm returning all the columns for the column family PRF where the date matches May 1st, 2014. Having looked at what HBase is all about, its differences from relational databases and Hadoop, its architecture and data model, there are some conclusions I draw. Use HBase for random read, random write, or both on large data sets. It is best used for thousands of operations per second on terabytes of data. It is used for well-known and simple access patterns. HBase is not suited for data exploration and ad hoc analysis activities. HBase key design is extremely important because it is designed for access patterns. There would be some data redundancies in HBase, again because it is designed for access patterns and the same data set can be accessed for different patterns. HBase guarantees atomicity at row level. HBase seems to be a system for programmers and not really for data analysts because it does not provide a SQL-like interface. However, This limitation can be overcome by creating Hive external tables on HBase and making HQL available for data analysts, or even putting a BI tool on top of Hive tables with a Hive connector. Some of the natural steps, next steps would be, for me, would be to load data in bulk via a MapReduce program or a pig script, run HBase in a distributed mode, and also try using external tables, Hive external tables on top of HBase for query-like access, or instead use Avro or Thrift clients. I thank you for your time for sitting through this presentation, and I hope this was useful.